Okay, back in chapter 12 in Cal 2, you learned that if you had a two-dimensional vector function, r of t, g of t, that the length of the arc from a to b, where t values are a to b, was the integral from a to b of the square root of f prime of t squared plus g prime of t squared. Okay, now that definition can be extended if you have a vector valued function in 3 dimensions. So given some vector valued function f of t, g of t, h of t, then the arc length will be given by this. So it's just the integral from a to b of f prime of t squared plus g prime of t squared plus h prime of t squared. And since that is also just the magnitude of the velocity vector, you could also write it as a shorthand way of saying the magnitude of r prime of t. Okay, because if r of t is f of t, g of t, h of t, then r prime of t is the f prime of t, g prime of t, h prime of t. And so the magnitude of r prime of t looks just like that integrand. Okay, so we can write that integral for the arc length either way, from a to b, the square root of f prime of t squared plus g prime of t squared plus h prime of t squared, or simply magnitude of r prime of t dt. Okay, and that'll come in handy a little bit later in this lesson. Okay, what I want to look at now is I want to look at finding the arc length for trajectories of some of the planets, for some of the paths that they take. So Kepler's first law says that the planets revolve around the sun in elliptical orbits. Okay, so a vector function that describes an ellipse would be of this form. So that's what an ellipse would look like. Very similar to the circle, but you don't have the same numbers in front of the cosine and sine. So the a, if a is the longer of the two, that's that distance here. It's half the length of the major axis, and the distance b is half the length of the minor axis. Okay, so now what I want to look at is I want to find what the lengths of the orbit will be using our formula. So I'm going to look at one particular planet. Let's look at Mercury. It says that they give us what the A value is, they give us what the B value is. And notice here the A's and the B's are very similar, so these are almost circular orbits. They also look at they give us another value, alpha, which is the B over A. So if you just take B divided by A, that's going to be something we're going to use in just a minute. So I have that A is 0.387, and B is 0.379, and alpha is 0.979 for Mercury. So let's go back and see if we can find the arc length. Okay, so what I'm going to do is I'm going to find the arc length, and I'm going to assume that it's in this path, this elliptical path. It's going to be the integral from 0 to 2 pi, the square root, and I'm going to find r prime of t, which will be negative a sine of t, b cosine of t. So we're going to have negative a sine of t squared plus b cosine of t squared dt. I'm doing it in general, and I'll plug in the a and the b values later. Okay, so this is a squared sine squared plus b squared cosine squared. Okay, Now, what I'm going to do just to simplify this a little bit is to pull out a squared. So pulling it out of the square root, I'll have an a out in the front. And then that's going to force this to be b over a. So it's just to make the function a little bit cleaner on the inside when we work with it. That table gave us the specific values for alpha. We had that alpha was equal to 0.979, and that was the b over a. And this is for a equal 0.387. This is for mercury. Okay. Okay, so now because this is also, we have a symmetrical path, we could also just evaluate it from 0 to pi over 2 and multiply it by 4. Notice I'm changing the upper limit here. Okay, instead of b over a here, I'm just going to change it to alpha just to. Okay, so now I need to evaluate this. So let me pull up my calculator. Hopefully you can see it. Okay, first thing I need to do is enter this function. Notice this is not an integral that can be simplified, using elementary functions. So the only way we're going to be able to figure out the magnitude of this, or evaluate this, is to use some sort of software technology to do it. I'm going to just use the integral function on my calculator. First thing I need to do is enter the function, which is going to be the integrand. So y equal, and I'm going to put the square root of sine squared. I want to make sure sine is squared, so I'm going to put parentheses around it. Squared plus alpha squared. I'm going to go ahead and plug in alpha. Alpha is 0.979. Squared. And then we're going to multiply that by cosine squared. I'm putting cosine of t squared. Okay, and then I'm closing my parentheses for the square root. So that should be the integrand. And now I just want to integrate from 0 to pi over 2, and then I'll multiply it by 4 times the a at the end. And hopefully then we have the length of the orbit for Mercury. So go to calculate, pick option 7. I'm going to draw a graph. Now this is the graph of this square root function, so it doesn't mean a whole lot to us. The lower limit will be the t value of 0, so enter. The upper limit will be the pi over 2, so pi divided by 2, enter. So it showed me the area, so we just are finding the area under that curve. And then I need to multiply it by 4 times the a, so times 4 times, and our a was 0.387. Okay, so we get 2.406. Okay, and that should be the length of the orbit for Mercury. So now if I look at this the table on this next page, you see here, there's the orbit length for Mercury that we found using our formula. Okay, and so you could repeat that for any of the planets that you were interested in. Okay, now let's look at one more example. I've got a vector valued function that's given me the path of an eagle. Okay, it says it's rising at the rate of 100 vertical feet per minute on this elliptical path. Elliptical path. It's a helix, creates a helix. I want to find the arc length. And I know the formula, this is a three-dimensional vector valued function. So the arc length will be the interval from a to b, so whatever the values of t are that we're interested in. And then we're going to find f prime of t squared plus g prime of t squared plus h prime of t squared. Okay, so let's find f, g, and h. The f is 250 cosine, so let's see, r prime of t will be negative 250 sine. Then we have 250 cosine, and then we have 100. Okay, so plugging those in, that we're interested in how far it travels in 10 minutes, so that would be from t equals 0 to t equals 10. So we have 250 sine squared, all of it squared, plus 250 cosine plus 100 squared. Okay, so we're going to have 62,500 sine squared cosine squared Okay, now when you factor out 62,500 from sine squared and cosine squared, you get sine squared plus cosine squared, which is just 1. So this just ends up being the square root of 62,500 plus 10,000. So this is going to be just 72,500 t from 0 to 10. So this times 10, we'll put the 10 in the front. Which this is approximately, 269 is approximately the square root of 72,500, and then times that extra 10. Okay, so that gives the approximate number of feet that the Eagle has flown in 10 minutes.